For flexible payments, we need to calculate the allowable ESA per actual group and SAR per ESA. Afterwards, we need to calculate the design ESA and design SAR for each distress type. And then we can make a comparison of these allowable and design values. If we want to convert the design traffic loading units in HVAG and SAR, and vice versa, we need to use the damage indices, ESA over HVAG, SAR over HVAG, and SAR over ESA. This is the triangle relationship between NDT in HVAG, NDT in ESA, and NDT in SAR. Then you may ask, why using different units? This is because the allowable traffic is normally expressed in terms of ESA or SAR. So we need to use these relationships to make the conversion. The payment design by mechanistic method, how to consider appropriate types of damage. In design of granular payments with thin bituminous surfacing, only one type of damage is considered, namely the overall deterioration of the pavement, reflecting the increased level of roughness and rotting. So however, for pavements containing one or more bond layers, up to 3 distinct types of damage are considered. The fatigue damage to asphalt SAR5, the rotting and loss of surface shape SAR7, and fatigue damage to cemented material SAR12. They are the allowable traffic calculated using the damage models in SAR units. The damage and distress models for different material types are shown below. So we have seen these formulas in lecture 7. The allowable traffic from these damage models are expressed in units of SAR5, SAR7, or SAR12, corresponding to this component of damage model M. So if we equal those doubles, then mu epsilon doubles. Correspondingly, from these damage models, the N decreases by the ratio of 2 to the power of M, and damage increases by the ratio 2 to the power of M. You may think, if all actual groups in traffic are identical and impose the standard actual load, then there's no need for different units. But real situation is far more complex, as traffic has different combination of actual group loadings. Say traffic has 3 actual group loadings. First group carries 0.5 standard load. Second group carries 1 standard load, and third group 2 standard load. It is obvious the same traffic imposes different damage in terms of total SL to different materials based on the damage models. So from this table, we are able to work out the total damage to different materials from these 3 different actual groups. The pavement structural design carries the allowable traffic loading repetitions are greater than or equal to the design traffic loading repetitions. So comparison needs to be based on the consistent units, the ESA or SAR5 or SAR7 or SAR12 for all possible damage or distress failure modes. If the units are not consistent, then we need to convert the units of the design traffic loading. So here we introduce the concept of standard actual. The equivalent standard actual ESA was developed as an index of loading to express permanent damage caused by all these actual group loads of various actual. So ESA isn't a physical identity itself, it's an index of loading that enables you to look at the combined damage of different actual group loads and tears. And it expresses that damage in terms of equivalent passes was standard actual. So in the flexible payment design process, the first step in assessing the ability of a payment configuration to withstand the design traffic is to determine the extent of damage caused to the configuration by a reference actual group termed the standard actual. As shown on the slide, here is the definition of standard actual. The standard actual is a single actual with two tears. And a load of 80 kilonewton on the actual. The standard actual is the reference damage load. So loads on different actual configuration with dual tears that cause the same amount of damage as the standard actual are contained in this the right table. So for example, 181 kilonewton on a triaxial with dual tears causes the same rotting damage as 80 kilonewton on our single standard actual. So designs are based on equivalent number of standard actuals. Damages of all other actual loadings are referenced to it as the number of equivalent standard actual repetitions. Previous table is for standard actual from dual tears. Loads on actual groups with single tear, which cause the same damage as the standard actual is shown in this table. And the load varies with the actual group type and nominal tear section widths. Actual load from these actual groups is the equivalent of one standard actual repetitions, SAR. To calculate the SAR of damage, a procedure is required to calculate the damage associated with each actual group of each actual type in the traffic load distribution relative to the damage caused by a standard actual. The loads on actual configurations that causes the same amount of damage as the standard actual could be referred from the above two tables. For each actual group carrying a certain load Lij, it could be converted into an equivalent number of standard actual repetitions or a specific type of damage characterized by damage exponent M as the following equation. So in this equation, SAR Mij is the number of standard actual repetitions, which causes same amount of damage as a single passage of actual group I with load Lij, where load damage exponent is M. As Li is the standard load for actual group I, we can refer to the values in previous two tables. The Lij is the J's load magnitude for actual group type I, and M is the load damage exponent for different damage type. The M exponent in the above equation is taken from table 7.7. So for empirical design of granular pavement with seam bituminous surfacing and for overall pavement damage, M equal to 4, and the damage unit is ESA. Within the mechanistic design of pavement with one or more bond layers, the fatigue damage of asphalt has a damage exponent of 5 and damage unit of SAR5. While rotting and loss of surface shape has damage exponent of 7 and damage unit of SAR7. The fatigue damage of cemented materials has damage exponent of 12 and damage unit of SAR12. So during design, we need to calculate the total ESA or SAR for each relevant damage type using the parameter M in this table. From equation 16, we can see that damage increases exponentially with load. For example, the actual load carrying twice the load of standard actual causes the same damage as 2 to the power of m standard actual repetitions, as shown here. Now let's look at one example to determine the damage indices using equation 16 for a road pavement based on the collected data shown in traffic load distribution table H1. The damage indices, in other words, ESA over HVAG, SAR over HVAG, and SAR over ESA, project based and vary for specific road and traffic load distribution. The left is the project traffic load distribution table. So the first column is the magnitude of actual group load. The other columns are the percentage of each actual group type for different actual group load. The total proportion of each actual group is 1. The red table is the project traffic load distribution by proportion of actual groups of each type and load. For example, the project traffic load for actual group of 10 kilonewton and actual group type of SAST is calculated as 0.2569 divided by 100 times 0.3799, and we get a value of 0.000976. Then we are able to calculate the SAR for damage exponent of 4, 5, 7, and 12 according to equation 16. For granular pavement with thin surfacing, M equal to 4. For asphalt fatigue damage, M equal to 5. So for the first value in the bottom line of the left table, the SAR is calculated as 400 divided by 53. Because it is single actual with single tear SAST, and nominal tear section width is less than 375 millimeter. So the standard actual load is 53 kilonewton here. And when it plugged into this formula, we get a value of 3,244.4. Similarly, the SAR for rotting a loss of surface shape is M equal to 7, while SAR for fatigue of cemented materials is M equal to 12. We are able to calculate the corresponding SAR as well, and they are summarized in those tables. The table H4 is SAR multiplied by the proportion of each actual group load of each actual group type in the project traffic load distribution. In other words, table H4 equals to table H2 times table H3 with damage exponent of 4, 5, 7, and 12. For example, for actual group load of 140 kilonewton and actual group type of SAST and damage exponent of 4, the value is 2.01 times 10 to the power of -5 times 48.687. So both values are taken from the previous two tables, table H2 and table H3, and finally we get a value of 0.00098. The sum of the entries in this table is 0.8. and that's ESA over HVAG. Similarly, the average SAR5 over HVAG for M equals to 5 is the sum of the calculated values in the right table, and it is 0.96. So similarly, for the damage exponent of 7 and 12, the damage index SAR7 over HVAG and SAR12 over HVAG are calculated and shown in these tables. From previous table H1 to H4, the damage index values are summarized in table H5 below. The indices represent the damage in terms of ESA or SAR per HVAG of project traffic for each damage type. Based on these indices, we are able to convert the traffic loading from one unit to another. Now let's look at one example to see how to calculate the design traffic in terms of ESAs and SARs and how the conversion is done. We could use traffic data from example 3 and the project specific WIM data from example 4 and tables H1 to H5 to estimate the standard actual repetitions per ESA and determine the design ESA and SAR for the relevant damages. If we divide SAR over HVAG by ESA over HVAG, then we get the SAR over ESA values as shown in table H6. So if we know the values of the damage index, we could convert the traffic units from ESA to SAR or the other way around. The design traffic loading is normally expressed in ESAs or SARs. So if we know the design traffic loading NDT in HVAG and the damage index for flexible payment, then the design traffic loading NDT in ESA could be calculated as DSA equals to NDT times ESA over HVAG equals to 2.9 times 10 to the power of 6 times 0.8, and we get a value of 2.3 times 10 to the power of 6 ESA. So DESA is NDT in ESA units. Similarly, the SAR5 is NDT in SAR5 units. The SAR7 is NDT in SAR7 units, and the SAR12 is NDT in SAR12 units. Apart from DSA, if we want to calculate DSAR5, DSAR7, and DSAR12 for flexible payment, we're able to multiply the DSA by the corresponding SAR or ESA values from table H6. The resulting values are given in table H7. Another way of calculating the SAR is to multiply the NDT by average SAR per HVAG in table H5. For example, the SAR7 equals to 2.9 times 10 to the power of 6 times 1.67, and we get which is the same value as the one in the table above.